Chapter 3, Section B, Biological Bases of Behavior. In a jar on a display shelf in Cornell University's Psychology Department resides the well-preserved brain of Edward Bradford Titchener, a great turn-of-the-century experimental psychologist and proponent of the study of consciousness. Imagine yourself gazing at that wrinkled mass of grayish tissue and wondering if in any sense Titchener is still there. You might answer that, without the living whir of electrochemical activity, there could be nothing of Titchener in his preserved brain. Consider then an experiment about which the inquisitive Titchener himself might have daydreamed. Imagine that just moments before his death, someone removed Titchener's brain from his body and kept it alive by floating it in a tank of cerebral fluid while feeding it enriched blood. Would Titchener still be in there? Further imagine that someone then transplanted the still living brain into the body of a person with severe brain damage. To whose home should the recovered patient return? That we can imagine such questions illustrates how convinced we are that we live somewhere north of the neck, as Fodor said in 1999. And for good reason. The brain enables the mind, seeing, hearing, smelling, feeling, remembering, thinking, speaking, dreaming. The brain is what poet Diane Ackerman, in 2004, page 3, calls that shiny mound of being, that dream factory, that huddle of neurons calling all the plays, that fickle pleasure-drome. Moreover, it is the brain that self-reflectively analyzes the brain. When we're thinking about our brain, we're thinking with our brain, by firing countless millions of synapses and releasing billions of neurotransmitter molecules. The effect of hormones on experiences such as love reminds us that we would not be of the same mind if we were a bodiless brain. Brain plus body equals mind. Nevertheless, say neuroscientists, the brain enables the mind. If all your organs were transplanted, you would still be much the same person, unless, as psychologist Jonathan Haidt has said, one of those organs was the brain. But precisely where and how are the mind's functions tied to the brain? Let's first see how scientists explore such questions. "I am a brain, Watson. The rest of me is a mere appendix," said Sherlock Holmes in Arthur Conan Doyle's The Adventure of the Mazarin Stone. Section 3B.1. The Tools of Discovery. Having our head examined. How do neuroscientists study the brain's connections to behavior and mind? For centuries, we had no tools, high-powered yet gentle enough to explore the living human brain. Clinical observations of patients revealed some brain-mind connections. Physicians noted, for example, that damage to one side of the brain often caused numbness or paralysis on the body's opposite side, suggesting that the body's right side is wired to the brain's left side and vice versa. Others noticed that damage to the back of the brain disrupted vision, and that damage to the left front part of the brain produced speech difficulties. Gradually, these early explorers were mapping the brain. Now, within a lifetime, the whole brain mapping process has changed. The known universe's most amazing organ is being probed and mapped by a new generation of neural cartographers. Whether in the interests of science or medicine, they can selectively lesion, destroy, tiny clusters of normal or defective brain cells, leaving the surrounding tissue unharmed. Such studies have revealed, for example, that damage to one area of the hypothalamus in a rat's brain reduces eating, causing the rat to starve unless force-fed. Damage in another area produces overeating. Today's scientists can also electrically, chemically, or magnetically stimulate various parts of the brain and note the effects, snoop on the messages of individual neurons, and eavesdrop on the chatter of billions of neurons, and see color representations of the brain's energy-consuming activity. These techniques for peering into the thinking, feeling brain are doing for psychology what the microscope did for biology and the telescope did for astronomy. Let's look at a few of them and see how neuroscientists study the working brain. Section 3B.1.1. Recording the brain's electrical activity. Right now, your mental activity is giving off telltale electrical, metabolic, and magnetic signals that would enable neuroscientists to observe your brain at work. The tips of modern microelectrodes are so small they can detect the electrical pulse in a single neuron. For example, we can now detect exactly where the information goes in a cat's brain when someone strokes its whisker. Electrical activity in the brain's billions of neurons sweeps in regular waves across its surface. An electroencephalogram, EEG, is an amplified readout of such waves. Studying an EEG of the brain's activity is like studying a car engine by listening to its hum. By presenting a stimulus repeatedly and having a computer filter out brain activity unrelated to the stimulus, one can identify the electrical wave evoked by the stimulus. Figure 3.12. Section 3B.1.2, Neuroimaging Techniques. You must look into people as well as at them, advised Lord Chesterfield in a 1746 letter to his son. Newer windows into the brain give us that Superman-like ability to see inside the living brain. For example, the CT, computed tomography scan, examines the brain by taking X-ray photographs that can reveal brain damage. Even more dramatic is the PET, positron emission tomography scan, figure 3.13, which depicts brain activity by showing each brain area's consumption of its chemical fuel, the sugar glucose. Active neurons are glucose hogs. After a person receives temporarily radioactive glucose, the PET scan detects where this food for thought goes by locating the radioactivity. Rather like weather radar showing rain activity, PET scans hotspots show which brain areas are most active as the person performs mathematical calculations, looks at images of faces, or daydreams. In MRI, magnetic resonance imaging brain scans, the head is put in a strong magnetic field, which aligns the spinning atoms of brain molecules. Then, a radio wave pulse momentarily disorients the atoms. When the atoms return to their normal spin, they release signals that provide a detailed picture of the brain's soft tissues. MRI scans are also used to scan other body parts. MRI scans have revealed a larger than average neural area in the left hemisphere of musicians who display perfect pitch. Schlag et al. In 1995. They have also revealed enlarged fluid-filled brain areas in some patients who have schizophrenia, a disabling psychological disorder. Figure 3.14. A special application of MRI, fMRI, functional MRI, can reveal the brain's functioning as well as its structure. Where the brain is especially active, blood goes. By comparing MRI scans taken less than a second apart, researchers can watch the brain light up with increased oxygen-laden blood flow as a person performs different mental functions. As the person looks at a scene, for example, the fMRI machine detects blood rushing to the back of the brain, which processes visual information. See figure 3.25. Such snapshots of the brain's changing activity provide new insights into how the brain divides its labor. To be learning about the neurosciences now is like studying world geography while Magellan was exploring the seas. This truly is the golden age of brain science.